Let's step back to 1879 in the small German town of Ulm, where a baby named Albert Einstein is born. A year later, his family moves to Munich, where his dad, Hermann, and Uncle Jacob start a small business selling electrical gadgets. It wasn't exactly a booming startup, more like a struggling side hustle. Growing up, young Albert wasn't the kid you'd peg as a future genius. He was quiet, a bit of a dreamer, and didn't exactly light up the classroom. But those stories about him flunking school? Total myth. He was actually pretty sharp, just not a fan of strict teachers or rote learning. Fast forward to 1894, when Albert was a teenager. His dad's business goes bust, and the family relocates to Milan, Italy. His parents tell him to stay behind in Munich to finish high school. Yeah, right? Albert wasn't having it. He ditches school, hops a train, and joins his family in Italy. Talk about teenage rebellion. Later, he gets his act together and enrolls in a top-notch technical school in Zurich, Switzerland, graduating in 1900. But here's the thing. Albert was a bit of a contrarian. He loved arguing, questioning authority, and thinking outside the box. His professors? Not so thrilled. They didn't offer him a teaching gig, which was the usual path to a science career back then. So, what's a young, jobless genius to do? In 1902, Albert lands a desk job at the Swiss Patent Office in Bern. It's not glamorous. Think piles of paperwork and patent applications for quirky inventions. But it gave him time to think. And boy, did he think big. In 1905, while still a patent clerk, Albert publishes 3 papers that flip the world of physics upside down. These papers make him a rock star in the science world and spark 2 massive revolutions in how we understand time, space, and reality itself. To get why Einstein's ideas were such a big deal, let's rewind to the late 1800s. Scientists back then thought they were this close to cracking the code of the universe. They had a theory that space was filled with something called the ether, an invisible, jelly-like substance that carried light and radio waves, kind of like how air carries sound. They figured all they needed was to measure how stretchy this ether was, and they'd have the universe all figured out. Here's a fun tidbit. When Harvard built its Jefferson Laboratory, they went all out to avoid using iron nails. Why? They wanted to do super precise experiments on magnets without any metal interference. But, oops, they forgot the red-brown bricks they used for the building, and most of Harvard were loaded with iron. Talk about a facepalm moment. That building's still standing, but they're not 100% sure the library floor, built without iron nails, can hold up. Anyway, the ether idea had a problem. Scientists thought that if you moved through the ether, light's speed should change depending on your direction, like how wind feels stronger or weaker depending on whether you're biking with it or against it. If you're moving in the same direction as light, it should seem slower. Move the opposite way, and it should seem faster. But experiments kept showing this wasn't true, and it was driving scientists nuts. Enter the Michelson-Morley experiment of 1887, conducted in Cleveland, Ohio, at what's now Case Western Reserve University. Albert Michelson and Edward Morley were like the Sherlock Holmes and Dr. Watson of physics, trying to crack the ether case. They set up a clever device called an interferometer, which split a beam of light into 2 parts, sent them in perpendicular directions, and then recombined them. The idea was that if the ether existed, the light beams would travel at different speeds because the Earth was moving through the ether as it orbited the Sun and spun on its axis. One beam should lag behind the other, creating a pattern of interference, like ripples canceling each other out in a pond. But here's the kicker. They found no difference in the light beam's speeds. None. Zilch. Whether it was day or night, summer or winter, the light moved at the same speed no matter what. It was as if the ether wasn't even there. This result was a head-scratcher, shaking up the physics world like a plot twist in a blockbuster movie. 2 scientists, George Fitzgerald from Ireland and Hendrik Lorentz from the Netherlands, tried to save the ether idea. They suggested that when objects move through the ether, they shrink a tiny bit, and clocks slow down just enough to make light's speed look constant. It was a clever workaround, but they still clung to the idea that the ether was real. Then comes Einstein in 1905, fresh off his patent office desk, with a bold new take. In one of his groundbreaking papers, he says, "Forget the ether. It's not needed." His reasoning? If you can't tell whether you're moving through the ether or not, then the whole concept is useless. Instead, he proposes something wild. The laws of physics are the same no matter how fast you're moving, and the speed of light is always constant, about 186,000 miles per second, whether you're standing still or zooming through space. This idea sounds simple, but it's a game changer. To make it work, Einstein had to throw out the idea of universal time. You know how we assume time ticks the same for everyone, everywhere? Nope. Einstein said time is personal. If you're moving relative to someone else, your clock runs differently. Say you're on a train and your buddy's on the platform. Your watch might tick a tiny bit slower than theirs, though you'd need to be moving crazy fast to notice. This was proven in real experiments. For example, scientists took super-accurate clocks, put them on planes, and flew them around the world in opposite directions. When the planes landed, the clocks showed slightly different times, just as Einstein predicted. Want to live a fraction of a second longer? Book a flight east, so your speed adds to the Earth's rotation. But don't expect much. The jet lag and airplane food will probably make you feel like you've aged a decade. Einstein's theory, called special relativity, got its name because it's all about relative motion, how things look depending on how you're moving compared to something else. It's elegant, simple, and mind-blowing, like a perfect pop song that changes music forever. But not everyone was a fan. Back then, scientists were married to two big ideas: the ether as a kind of absolute resting state of the universe and the notion that time was the same for everyone. Einstein's theory smashed both, and some folks weren't happy. They even worried it meant everything's relative, including morals, which freaked them out. Despite the haters, special relativity won over the science world. It's been tested countless times and powers modern tech, like GPS, which needs to account for time differences caused by satellites moving super fast in orbit. Einstein got the Nobel Prize in 1921, but, not gonna lie, it wasn't for relativity. The committee gave it to him for a different 1905 paper on something called the photoelectric effect. More on that later. They thought relativity was too controversial. Even today, I get emails a few times a week claiming Einstein was wrong. Spoiler, he wasn't. The evidence is overwhelming. One of the coolest things to come out of special relativity is the equation everyone knows: E equals mc squared. In plain English, it says energy E and mass m are two sides of the same coin, connected by the speed of light squared, c superscript 2. It's like saying a dollar bill and 4 quarters are worth the same. They're just different forms of the same thing. This equation is a big deal because it means if you convert a tiny bit of mass into energy, you get a huge amount of energy. For example, when a uranium nucleus splits in a nuclear reaction, the resulting pieces weigh just a smidge less than the original. That tiny bit of lost mass turns into a massive burst of energy. Think of it like a magic trick. A small pebble disappears, and poof, you get a fireworks show. This idea became super important in 1939, right before World War II. A few scientists realized this could lead to powerful bombs. They convinced Einstein, a lifelong pacifist, to sign a letter to President Franklin D. Roosevelt, urging the U.S. to start nuclear research. Einstein's name carried weight, and that letter helped kick off the Manhattan Project, which built the atomic bombs dropped on Hiroshima and Nagasaki in 1945. Now, some folks blame Einstein for those bombs because he figured out E equals mc squared. That's like blaming the guy who invented the wheel for a car crash. Einstein didn't work on the Manhattan Project and was horrified by the bombings. He just uncovered a truth about the universe. How people used it was out of his hands. According to special relativity, time isn't the same for everyone. This leads to something called the twin paradox. Take twin brothers, Alex and Ben. Alex blasts off in a spaceship, traveling close to the speed of light, while Ben stays on Earth. Because Alex is moving so fast, time on his spaceship slows down compared to Ben's time. When Alex returns, he's younger than Ben, who's now rocking a few extra wrinkles. Sounds like science fiction, right? But it's real. Experiments with fast-moving particles and those plane-flying clocks confirm it. Time slows down when you're speeding along, though you'd need to hit near-light speeds for it to be noticeable in everyday life. It's not exactly a fountain of youth, but it's a glimpse into how flexible time really is. Let's zoom in on that E equals mc squared idea again. Inside an atom's nucleus, protons and neutrons are held together by a super strong force. But the nucleus weighs less than the sum of its parts. That missing mass is the binding energy, like the glue holding the nucleus together. When a nucleus like uranium-235 splits, that energy gets released big time. It's what powers nuclear reactors and, yes, those devastating bombs. This splitting can start a chain reaction. One neutron hits a uranium nucleus, causing it to split and release more neutrons, which hit other nuclei, and so on. If it keeps going, you've got a critical reaction. Boom. The amount of uranium needed to sustain this is called the critical mass. It's like setting off a line of dominoes that just won't stop. By 1905, Einstein, the patent clerk with a rebellious streak, had turned physics on its head. He ditched the ether, showed time and space aren't what they seem, and revealed that mass and energy are interconnected. His ideas didn't just change science. They paved the way for technologies we rely on today and raised big questions about the universe. But this is just the start. Einstein's journey and his theories get even crazier from here. After shaking up the science world with his 1905 papers, Albert Einstein was no longer just a patent clerk with big ideas. His reputation was growing, but it took a few years for the academic world to catch up. In 1909, he finally landed a teaching job at the University of Zurich, letting him ditch the patent office desk. 2 years later, he moved to the German University in Prague, but by 1912, he was back in Zurich, this time at his old school, the Polytechnic. Despite anti-Semitism being a real issue in European universities back then, Einstein's brilliance was hard to ignore. Offers started rolling in from places like Vienna and Utrecht, but he chose a research gig at the Prussian Academy of Sciences in Berlin. Why? It meant no teaching duties, just pure research, his dream setup. In April 1914, he moved to Berlin, and his wife, Maliva, and their 2 sons joined him. But things at home weren't great. The marriage was rocky, and soon Maliva and the kids moved back to Zurich. Einstein visited them occasionally, but the marriage didn't last. He later divorced Maliva and married his cousin Elsa, who lived in Berlin. Maybe the lack of family drama during World War I, when he was living the bachelor life, helped him focus. Whatever the reason, those years were a goldmine for his scientific work. Now let's talk about Einstein's next big leap, gravity. His special relativity theory from 1905 worked great for things like electricity and magnetism, but it clashed with Isaac Newton's law of gravity. Newton said that if you move a heavy object somewhere in space, its gravitational pull instantly affects everything else in the universe, no matter how far away. Sounds cool, but it breaks special relativity's rule that nothing, not even gravity, can travel faster than light, which is about 186,000 miles per second. Plus, Newton's idea relied on a universal clock ticking the same for everyone, which Einstein had already shown was nonsense. Time is local, not universal, so instantly doesn't even make sense. Einstein started puzzling over this back in 1907, while still at the patent office. By 1911, in Prague, he was diving deep into the problem. He had a light bulb moment. Gravity and acceleration are two sides of the same coin. Think of being in an elevator. If it's sitting still on Earth, you feel gravity pulling you down. If it's in space and a rocket's accelerating it upward, you feel the same push against the floor. You can't tell the difference without looking outside. Einstein realized this connection was key. Before spaceships were a thing, he pictured elevators, not starships. Sorry, no Star Trek vibes yet. But there's a catch. You can only accelerate or free fall in an elevator for so long before you hit something, like the ground or the ceiling. On a flat Earth, you could argue an apple falls on your head because gravity pulls it down or because the ground is accelerating up to meet it. But on a round Earth, that logic falls apart. People on opposite sides would be accelerating in different directions yet staying the same distance apart, which doesn't add up. This idea led Einstein to his general theory of relativity, published in 1915. It's a mind-bender, so let's break it down. Instead of gravity being a mysterious force pulling things together, Einstein said it's about space and time bending. Picture space and time like a stretchy trampoline. Drop a bowling ball on it, and it sags, creating a dip. Roll a marble nearby, and it'll curve toward the bowling ball because of that dip. That's how gravity works. Massive objects like planets or stars warp the fabric of space and time, and other objects follow those curves. When you toss a ball, it arcs back to Earth because Earth's mass bends space-time around it, guiding the ball's path. This was a radical idea. Newton's gravity was like an invisible string pulling objects together instantly. Einstein's gravity was about the shape of space itself, and those effects move at the speed of light, not faster. To test this, Einstein made a bold prediction. Light from a distant star should bend as it passes near the sun, because the sun's mass warps space-time. In 1919, during a solar eclipse, British scientist Arthur Eddington led an expedition to measure this. They watched stars near the sun's edge, and sure enough, their light bent exactly as Einstein predicted. When the news hit, Einstein became a global superstar overnight. Newspapers called it a revolution in science. General relativity wasn't just a theory, it was a new way to see the universe. But let's zoom out for a second. Why does this matter to the average person? General relativity isn't just for rocket scientists. It's why GPS works. Satellites in orbit experience weaker gravity and move faster than clocks on Earth, so their time runs slightly differently. Without correcting for general relativity, your phone's navigation would be way off. Next time you're using Google Maps to find a coffee shop, think Einstein. There's a quirky side to this, too. Einstein's equations showed that gravity affects time itself. Near a massive object like a planet, time moves slower than in empty space. It's not something you'd notice in daily life, but it's real. Scientists have tested this with super precise clocks, one near the ground, another high up in a tower. The clock closer to Earth ticks a tiny bit slower. So, if you want to age a fraction of a second less, live on the top floor of a skyscraper. Of course, the elevator ride might make you rethink the whole plan. Einstein's general relativity also opened the door to wild ideas about the universe. If space-time can bend, what happens near something insanely dense, like a star that's collapsed into a tiny point? That's where black holes come in. They're so massive that they warp space-time so much, not even light can escape. Back then, black holes were just a theoretical idea, but today we've got pictures of them. Huge, dark monsters in space with gravity so strong it's like a cosmic vacuum cleaner. Einstein's work wasn't without drama. His ideas challenged everything scientists thought they knew, and not everyone was on board. Some clung to Newton's simpler view of gravity, like holding onto a flip phone in the smartphone era. Plus, Einstein's Jewish background didn't help in a Europe rife with anti-Semitism. Still, his ideas were too powerful to ignore. By the 1920s, he was a household name, but he kept pushing forward, wrestling with even bigger questions about the universe. General relativity also raised a big puzzle. If gravity is about space-time bending, what's the universe itself doing? Is it static, just sitting there, or is it moving? Einstein initially thought the universe was fixed, like a giant, unchanging bubble. To make his equations match this idea, he added a fudge factor called the cosmological constant, a kind of anti-gravity force to keep things stable. But in the 1920s, astronomer Edwin Hubble dropped a bombshell. The universe is expanding. Galaxies are moving away from each other, like dots on a balloon that's being inflated. Einstein scrapped the cosmological constant, calling it his biggest blunder. Funny thing is, scientists later brought it back to explain why the universe's expansion is speeding up. Einstein was ahead of his time, even when he thought he was wrong. This expanding universe idea led to another wild thought. If everything's moving apart, maybe it all started from a single point, a massive explosion we now call the Big Bang. Einstein wasn't totally sold on this, but his equations made it possible. They suggested the universe had a beginning, which was a lot to wrap your head around. If the universe started with a bang, what was before that? And what's it expanding into? Those questions still keep scientists up at night. Einstein's general relativity didn't just change how we see gravity, it reshaped our view of the cosmos. It predicted things like black holes and the Big Bang, long before we had evidence for them. It's like Einstein handed us a map to the universe, and we're still exploring it. But he wasn't done yet. His ideas about gravity clashed with another big field, quantum mechanics, the science of tiny particles. That conflict would haunt him for the rest of his career, and it's a story for another day. Let's not forget the human side of Einstein. While he was cracking the code of the universe, his personal life was messy. After his divorce from Mileva, marrying Elsa gave him some stability, but he was never the perfect husband type. His focus was on science, and during those war years in Berlin, he had the freedom to dive deep into his work. Maybe that's why he came up with such groundbreaking stuff. Less laundry, more physics. By the time general relativity was confirmed in 1919, Einstein was more than a scientist. He was a cultural icon. His wild hair, quirky personality, and revolutionary ideas made him the face of genius. But he didn't stop there. He kept asking big questions, like what the universe is made of and whether we can ever fully understand it. His work laid the foundation for modern cosmology, from black holes to the Big Bang, and it's still shaping how we explore space today. Einstein's work on gravity and space-time was a game-changer, but he didn't stop there. His ideas sparked big questions about the universe's size, shape, and future. Let's dive into what came next. His struggles with the universe's expansion, the birth of the Big Bang idea, and his uneasy dance with the weird world of quantum mechanics. After general relativity hit the scene in 1915, Einstein wrestled with what it meant for the cosmos. He initially thought the universe was like a giant, unchanging snow globe, fixed and eternal. To make his equations fit this steady-state idea, he tossed in a mathematical tweak called the cosmological constant. Think of it as a cosmic push to balance gravity's pull, keeping the universe from collapsing or flying apart. But then, in the 1920s, astronomer Edwin Hubble threw a curveball. Using powerful telescopes, he saw that galaxies were zooming away from each other, like cars scattering after a traffic jam. The universe wasn't static, it was expanding. Einstein reportedly called his cosmological constant his biggest blunder. kicking himself for not predicting this. Funny enough, decades later, scientists brought the constant back to explain why the universe's expansion is speeding up, thanks to something we now call dark energy. Einstein's mistake wasn't so mistaken after all. This expanding universe idea led to an even wilder thought. If everything's moving apart, maybe it all started from one superdense point. This is where the Big Bang theory comes in. A Belgian priest and scientist named Georges Lemaitre crunched the numbers using Einstein's equations and suggested the universe began with a massive explosion billions of years ago. Picture a cosmic firework, with all matter and energy bursting from a single speck. Einstein wasn't thrilled about this at first. He liked the idea of a timeless universe. But the evidence piled up, from Hubble's galaxy observations to the discovery of cosmic background radiation in the 1960s, like an echo of that ancient blast. Today, we peg the Big Bang at about 13.8 billion years ago, and it's the backbone of how we understand the universe's history. Einstein's equations also hinted at something else: black holes. These are places where gravity is so intense that nothing, not even light, can escape. Think of a star collapsing into a tiny point with so much mass, it's like a cosmic trapdoor. Back then, black holes were just a math puzzle, but now we've got photos of them: dark, shadowy rings in space that gobble up everything nearby. Einstein wasn't sure they were real, but his theory predicted them, and that's a testament to how far ahead he was. While Einstein was reshaping our view of the cosmos, another revolution was brewing: quantum mechanics. This is the science of the super tiny atoms, electrons, and particles smaller than a speck of dust. Quantum mechanics says these tiny bits don't follow the neat rules of everyday life. They can act like waves and particles, be in multiple places at once, and only decide what they're doing when you observe them. It's like a cosmic game of probability, and Einstein hated it. He famously said, "God does not play dice with the universe." He wanted a universe that made sense, where things followed clear rules, not one ruled by chance. Quantum mechanics started gaining steam in the 1920s, thanks to scientists like Niels Bohr and Werner Heisenberg. They showed that particles like electrons don't have exact positions or speeds until you measure them. It's as if a baseball could be both a ball and a wave until you swing a bat at it. Einstein clashed with Bohr in epic debates, arguing that there must be hidden rules making things predictable. He came up with clever thought experiments, like the EPR paradox, named after Einstein, Podolsky, and Rosen, to poke holes in quantum ideas. He suggested that if two particles are linked, measuring one could instantly affect the other, even light years away. This spooky action at a distance, as he called it, seemed to break his rule that nothing moves faster than light. But experiments years later, like those by John Bell, showed quantum mechanics was right. Particles can be weirdly connected like that. Einstein didn't live to see these results, but they confirmed the quantum world he doubted. This clash between general relativity and quantum mechanics is still a big deal. Relativity rules the big stuff: stars, galaxies, black holes. Quantum mechanics owns the tiny stuff: atoms, particles, subatomic bits. But when you try to mix them, like figuring out what happens inside a black hole, the math breaks down. It's like trying to combine a recipe for a cake with one for sushi. It just doesn't work. Scientists today are still chasing a theory of everything to bridge this gap, and Einstein's work is at the heart of that quest. Back to the universe's expansion, it raised another question. If the universe started with a big bang, what's its future? Will it keep growing forever, like a balloon that never pops? Or will gravity pull it back into a crunch, like squeezing a sponge? Einstein's equations allowed for both possibilities, depending on how much stuff, matter and energy, is out there. Today, we think the universe is about 27% matter, stars, planets, and mysterious dark matter, and 68% dark energy, with the rest being radiation. Dark energy, tied to Einstein's old cosmological constant, seems to be pushing the universe to expand faster and faster. So, no crunch. It's looking like an endless stretch. Einstein's unease with quantum mechanics didn't stop him from contributing to it. His 1905 paper on the photoelectric effect, which won him the Nobel Prize, showed that light comes in packets called quanta, a key piece of the quantum puzzle. It's ironic. He helped kickstart the very field he later fought against. That paper explained why light can knock electrons out of metal, like sunlight powering a solar panel. It's why we have things like digital cameras today. But for Einstein, quantum mechanics was too chaotic, too random. He spent his later years searching for a unified theory that would tie gravity and quantum mechanics together without all the weirdness. He didn't find it, but his quest inspired generations of physicists. The Big Bang idea also led to thoughts about time itself. If the universe had a start, what was before? Einstein's equations don't answer that. It's like asking what's north of the North Pole. Some scientists think time began with the Big Bang, while others wonder if our universe is just one bubble in a cosmic foam of many universes. These ideas were way out there in Einstein's time, but his work made them possible to consider. Black holes, too, keep popping up in this story. They're not just sci-fi monsters. They challenge our understanding of reality. Near a black hole, time slows down so much that if you watched someone fall in, from a safe distance, of course, they'd seem to freeze at the edge, their clock barely ticking. This is called the event horizon, the point of no return. Einstein's equations predicted this, but he wasn't sure such extreme objects existed. Today, we know they do, from massive ones at the centers of galaxies to smaller ones formed when stars burn out. Einstein's legacy in this part of the story is huge. He gave us tools to understand the universe's past, present, and future. The Big Bang Theory, black holes, and even the weirdness of quantum mechanics all trace back to his ideas. But he wasn't perfect. His resistance to quantum mechanics showed he could be stubborn, clinging to his vision of a predictable universe. Yet that stubbornness pushed science forward, forcing others to test and refine quantum ideas. And his blunder with the cosmological constant? It turned out to be a stroke of genius we're still unraveling. By the 1930s, Einstein was a global icon, but the world was changing. He fled Germany in 1933 as the Nazis rose to power, settling in the U.S. at Princeton. There, he kept working on his unified theory, debating quantum mechanics, and pondering the cosmos. His ideas about the universe's expansion and black holes were just starting to take shape, setting the stage for discoveries we're still making today. From GPS to pictures of black holes, Einstein's fingerprints are everywhere, even if he didn't always like where his ideas led. By the 1930s, Albert Einstein was a global legend, his wild hair and big ideas making him the face of science. His general theory of relativity had rewritten the rules of gravity, showing that massive objects like stars and planets warp the fabric of space and time, like a bowling ball sinking into a stretchy trampoline. But now, his work was pushing science into even stranger territory, the nature of time itself. Let's dive into how Einstein's ideas shook up our understanding of time, from Newton's simple clockwork universe to mind-bending concepts like singularities and the shape of the cosmos. Back in the 17th century, Isaac Newton had a straightforward view of time. To him, it was like a universal metronome, ticking steadily for everyone, everywhere, no matter what. Whether you were in London or on the moon, time marched on at the same pace, and everyone's clock would agree. Space was just a giant stage where things happened, and gravity was an invisible force pulling objects together. It was a tidy picture, like a well-organized spreadsheet, and it worked great for explaining things like falling apples or orbiting planets. Newton's laws let us predict where a cannonball would land or how the moon moves around Earth. For centuries, this was the bedrock of physics, and most folks thought it was the final word on how the universe worked. Then Einstein came along and flipped the script. His special relativity, from 1905, showed that time isn't the same for everyone. If you're speeding along in a rocket, your clock ticks slower than your friends back on Earth. It's not just a quirky idea. Experiments with super-accurate clocks on planes proved it. Fly east, and you might shave off a tiny fraction of a second compared to someone on the ground, though the airplane food might make you regret the trip. General relativity, from 1915, took things further. It said that gravity, like from a planet or star, also messes with time. The closer you are to a massive object, the slower time flows. Put a clock near Earth's surface and another high in a satellite, and the satellite's clock runs a bit faster. This isn't sci-fi. It's why GPS satellites need to adjust their clocks to keep your phone's navigation accurate when you're hunting for the nearest taco joint. This idea that time bends with gravity led to some wild possibilities. Near a super-dense object, like a collapsed star, time slows down so much it almost stops. These objects, called black holes, are where gravity gets so intense that space-time warps into a bottomless pit. If you got close to a black hole's edge, called the event horizon, you'd seem to freeze in time from an outsider's view, your clock barely ticking. Of course, you wouldn't notice anything weird yourself, but good luck getting out to tell anyone. Einstein's equations predicted these cosmic traps, though he wasn't sure they actually existed. Today, we've got photos of black holes, like the one at the center of our galaxy, looking like a glowing donut with a dark heart. They're real, and they're as freaky as Einstein's math suggested. But what happens inside a black hole? That's where things get really strange. Einstein's equations point to something called a singularity, a point where space and time break down completely. It's like the universe's math hits a divide by zero error. All the mass of a collapsed star gets squeezed into an infinitely tiny, infinitely dense speck. Time, space, and even the laws of physics stop making sense. Scientists like Roger Penrose and Stephen Hawking dug into this in the 1960s and 70s, building on Einstein's work. They developed theorems, fancy math proofs, showing that singularities are inevitable in black holes under general relativity. These Penrose-Hawking theorems are like a warning sign. Here be dragons. They tell us our understanding of the universe falls apart at these extreme points, and we need new physics to figure out what's going on. To wrap your head around this, think of the universe as a giant book. Most pages follow the rules of general relativity, describing how planets, stars, and galaxies move. But at a singularity, it's like the pages are torn out and the story stops. Penrose and Hawking showed that these blank spots aren't just in black holes. The Big Bang itself, the universe's explosive start 13.8 billion years ago, was likely a singularity too. If you trace the expanding universe backward, everything, matter, energy, space, time, gets crushed into a single, infinitely dense point. It's as if the universe's entire history began with a cosmic question mark. This raises a big puzzle. What was before the Big Bang? If time itself started there, asking what came before is like asking what's outside the edge of a map. Some scientists think the Big Bang was the absolute beginning, while others wonder if our universe is just one bubble in a cosmic soup of many universes. Einstein's equations don't give a clear answer, but they open the door to these mind-boggling questions. His work forced us to rethink time not as a straight line, but as something flexible, stretchy, and tied to the universe's structure. Now, let's zoom out to the shape of time across the cosmos. General relativity says the universe's geometry, its overall shape, depends on how much stuff, matter and energy, is in it. If there's a lot of matter, gravity could pull everything back together, like a rubber band snapping back, in what's called a big crunch. If there's not enough, the universe keeps expanding forever, like a balloon that never pops. Or it could balance perfectly, flat like a tabletop. In Einstein's day, no one knew which was true. He leaned toward a static universe at first, adding that cosmological constant to keep things steady. But Hubble's discovery of the expanding universe in the 1920s blew that idea out of the water. Today, we think the universe is about 27% matter, stars, planets, and mysterious dark matter, 68% dark energy, that cosmic push Einstein accidentally predicted, and 5% radiation. Dark energy seems to be winning, making the universe expand faster and faster, likely heading for an endless stretch rather than a crunch. This idea of time having a shape ties back to black holes and singularities. If you fell into a black hole, your time would end at the singularity, but for someone watching from far away, you'd never seem to reach it. Time gets warped in such extreme ways that it challenges everything we think we know. Einstein's equations let us model these effects, but they also show their limits. At singularities, the math breaks down, hinting that general relativity isn't the full story. Scientists like Hawking and Penrose suggested that quantum mechanics, the rules of the tiny, subatomic world, might hold the key to understanding singularities. But Einstein wasn't a fan of quantum mechanics, with its random, dice-rolling nature. He wanted a universe that followed clear, predictable rules, not one where particles could be in two places at once. Speaking of quantum mechanics, it's worth noting how it clashed with Einstein's view of time. In Newton's world, time was a steady drumbeat. In Einstein's, it's a rubber band, stretching and bending with motion and gravity. But in quantum mechanics, time gets even weirder. Particles can pop in and out of existence, and events don't always follow a neat cause and effect order. Einstein's battle with quantum mechanics, especially his debates with Niels Bohr, showed he wanted time and reality to make sense, not to be ruled by chance. Yet his own theories opened the door to these bizarre possibilities, like time slowing near a black hole or starting at the Big Bang. The Penrose-Hawking theorems also point to another freaky idea, the arrow of time. Why does time only move forward? Why don't we see coffee unspill or eggs unbreak? General relativity suggests the universe started in a highly ordered state at the Big Bang, with low entropy, a measure of disorder. As the universe expands, entropy increases, and that's why time has a direction, like a river flowing one way. Near a singularity, though, entropy and time get so jumbled that the rules might flip. Some scientists wonder if time could run backward in certain extreme conditions, but that's a puzzle we're still trying to solve. Einstein's work on time didn't just change science, it sparked our imagination. Movies like Interstellar lean heavily on his ideas, showing astronauts aging slower near black holes or wrestling with the vastness of cosmic time. But it's not just Hollywood. The practical side of Einstein's theories keeps our world running. Without general relativity, satellite communications, like your streaming service or weather forecasts, would fail because clocks in space tick differently than on Earth. Next time you binge a show or check the forecast, you're riding on Einstein's stretchy time. Back to singularities, they're not just cosmic dead ends. They challenge us to find a better theory, one that combines general relativity with quantum mechanics. Scientists call this the holy grail of physics, a theory of quantum gravity. In Einstein's time, this was a distant dream, but today we're closer, with ideas like string theory and loop quantum gravity trying to bridge the gap. These theories suggest that space and time might not be smooth but made of tiny, discrete bits, like pixels in a video game. If true, Singularities might not be infinite points, but fuzzy, quantum smears where the rules still hold. Einstein's legacy in rethinking time is huge. He showed it's not a universal clock, but a personal, flexible thing shaped by speed and gravity. His equations predicted black holes, singularities, and the Big Bang, long before we had telescopes or computers to confirm them. But he also left us with mysteries. What happens at a singularity? What was before the Big Bang? His work is like a map with some areas marked unknown, daring us to explore further. By the time he was at Princeton in the 1930s, Einstein was still chasing a unified theory to explain everything: gravity, time, particles, all of it. He didn't crack it, but his stubbornness pushed others to keep digging. The Penrose-Hawking theorems, built on his ideas, showed that singularities are real and unavoidable in our current understanding of the universe. They're like cosmic stop signs, telling us we need new physics to go further. Time, thanks to Einstein, isn't just seconds ticking by. It's a story of how the universe bends, stretches, and maybe even breaks. From GPS to black hole photos, his ideas shape our world and our questions about it. And as we'll see, the quest to understand time gets even wilder, with ideas about quantum gravity, wormholes, and maybe even time travel. Einstein's revolution was just the beginning. Einstein's work had already turned our understanding of time and space upside down. But science was charging into even stranger territory by the mid-20th century. His general theory of relativity explained the big stuff: stars, planets, black holes. But it didn't play nice with the rules governing the tiny world of atoms and particles. This clash led to a new frontier: quantum gravity, a quest to blend Einstein's ideas with the weird, probabilistic world of quantum mechanics. Let's dive into this wild ride, exploring how scientists tried to unify these theories, tossed around ideas like supersymmetry and string theory, and even flirted with the possibility of time travel. Quantum mechanics, that bizarre science of the supersmall, was a thorn in Einstein's side. It says particles like electrons can act like waves, exist in multiple states at once, and only pick a state when you measure them. It's like flipping a coin that's heads and tails until you look at it. Einstein couldn't stand this randomness, famously grumbling that the universe shouldn't work like a cosmic casino. But quantum mechanics was racking up wins, explaining things like how atoms emit light or why your phone's microchip works. The problem? When you tried to apply quantum rules to gravity, like inside a black hole, the math went haywire, spitting out nonsense answers like infinity. It's as if you asked a calculator to divide by zero and it started smoking. This mess pushed scientists to hunt for a theory of quantum gravity, a way to make relativity and quantum mechanics get along. Think of it like trying to merge two different video game worlds with incompatible rules. One big idea was supersymmetry, or SUSY for short. It's a theory that says every particle we know, like electrons or quarks, has a heavier, superpartner particle we haven't seen yet. These partners could balance out the math, making gravity and quantum mechanics work together. It's like adding a new ingredient to a recipe to stop it from curdling. Supersymmetry also promised to explain mysterious stuff like dark matter, that invisible material making up about 27% of the universe's mass. Scientists hoped to spot these superpartners in giant particle colliders, like the Large Hadron Collider in Switzerland. But so far, they've come up empty. Still, SUSY's a cool idea, and it's kept physicists busy for decades. Then there's string theory, an even wilder attempt to unify everything. Instead of particles being tiny dots, string theory says they're like tiny, vibrating strings. Think guitar strings, but a billion times smaller. Different vibrations make different particles, like playing different notes to create electrons, quarks, or even gravitons, hypothetical particles that carry gravity. String theory's big pitch is that it could explain gravity at the quantum level, smoothing out those pesky infinities. But there's a catch. It only works if the universe has extra dimensions beyond the three space dimensions: up, down, left, right, forward, back, and one time dimension we know. Some versions of string theory need 10 or even 26 dimensions, curled up so tiny we can't see them. It's like living in a house with secret rooms so small only ants could fit. String theory's elegant but tricky. No one's figured out how to test it directly, and it's more like a mathematical dream than a proven fact. Both supersymmetry and string theory aim to solve the same problem. What happens when gravity and quantum effects meet, like at the center of a black hole or during the Big Bang? Einstein's equations break down at these singularities, where space and time get crushed into an infinitely dense point. Quantum gravity theories suggest these points might not be infinite but fuzzy, like a pixelated image instead of a sharp dot. If space and time are made of tiny, discrete bits, like the pixels in a video game, then singularities might not be the dead ends Einstein's math predicted. This idea is still a work in progress, but it's a direct descendant of Einstein's challenge to understand the universe's deepest rules. Now, let's get to the really fun stuff: time travel. Einstein's equations don't forbid it, which is wild to think about. General relativity allows for weird setups where time could loop or bend in strange ways. One idea comes from black holes. If you could orbit a superdense, spinning black hole without getting sucked in, time would slow down so much that when you return to Earth, years or even centuries might have passed. It's not a DeLorean with a flux capacitor, but it's a kind of time travel into the future. Movies like Interstellar use this, showing astronauts coming back to find their kids all grown up. The math checks out, thanks to Einstein. But what about going backward in time? That's trickier. Einstein's equations allow for something called a wormhole, a shortcut through space-time, like a tunnel connecting two distant places or even two different times. Think of folding a piece of paper and poking a hole through it, so you can jump from one side to the other without crossing the whole page. If you could stabilize a wormhole, a big if, since they're super unstable, you might step through and end up in the past. The catch? You'd need exotic stuff, like matter with negative energy, to keep the wormhole open, and we're not even sure that exists. Plus, time travel raises headaches like the grandfather paradox. If you went back and stopped your grandpa from meeting your grandma, would you vanish? Einstein didn't have an answer, but his equations opened the door to these questions. Another time-bending idea comes from a guy named Kurt Gödel, a mathematician who worked with Einstein at Princeton. In 1949, Gödel found a solution to Einstein's equations where the universe rotates, creating paths called closed time-like curves. Follow one, and you'd loop back to your own past, like driving in a circle that takes you to yesterday. Gödel's universe doesn't match ours. We don't see the whole cosmos spinning, but it showed that general relativity allows for time loops in theory. It's like finding a glitch in the universe's code that lets you replay a level. These time travel ideas aren't just sci-fi fuel. They test the limits of Einstein's theories. If time travel is possible, it could mean the universe has built-in rules to prevent paradoxes, like making sure you can't mess with your own past. Some physicists think quantum mechanics might enforce these rules, acting like a cosmic referee. Others say time travel might only work in ways that don't change history, like you're destined to fail if you try to rewrite the past. It's all speculative, but Einstein's work made it okay to ask these crazy questions. Quantum gravity, supersymmetry, and string theory also tie into another big idea: the nature of space and time at the smallest scales. If string theory's right, space-time might not be smooth but grainy, like a digital photo zoomed in too far. This could change how we think about the Big Bang or black hole singularities. Instead of infinite points, they might be quantum fuzz, where time and space get blurry but don't break. These theories are still unproven, but they're built on the foundation Einstein laid, pushing us to rethink reality itself. Practically, these ideas have real-world impacts. Quantum mechanics, despite Einstein's doubts, powers tech like lasers, MRI machines, and the chips in your smartphone. String theory and supersymmetry haven't given us gadgets yet, but they inspire experiments at places like the Large Hadron Collider, where scientists smash particles to hunt for new physics. If we ever crack quantum gravity, it could unlock secrets about the universe's birth or even lead to tech we can't dream of today, like manipulating space-time for faster space travel. Einstein's work is the spark that keeps these fires burning. He spent his later years chasing a unified theory to tie gravity and quantum mechanics together, but he never found it. His stubbornness, though, lit a path for others. Supersymmetry and string theory are modern attempts to finish what he started, and they keep his legacy alive. Even his doubts about quantum mechanics pushed scientists to test it harder, making it stronger. And those time travel ideas? They're a reminder that Einstein's equations don't just describe the universe, they challenge us to dream bigger. By the time he was at Princeton, Einstein was a global icon, but he never stopped wrestling with these puzzles. His ideas about time, from its stretchy nature to its possible loops, reshaped science and culture. From black hole movies to particle colliders, his fingerprints are everywhere. The quest for quantum gravity and the possibility of time travel show that his revolution is far from over. It's just getting weirder. Einstein's journey through time, space, and gravity took us from his rebellious youth to mind-bending ideas about black holes and the Big Bang. Now, we're at the final stretch, tying up loose ends with a second look at the twin paradox, diving into cosmic strings, Gödel's time-bending universe, and big questions about the future of life, brain worlds, dark matter, and the universe's ultimate fate. This is the grand finale, where science gets weird, wild, and full of possibilities. Let's revisit the twin paradox, a quirky result of Einstein's special relativity. Say you've got twins, Sarah and Sam. Sarah hops on a spaceship and zooms off at nearly the speed of light, while Sam stays home, binge-watching his favorite shows. Because Sarah's moving so fast, time on her spaceship crawls compared to Sam's clock on Earth. When she returns after what feels like a few years to her, Sam's gone gray and has a whole collection of new streaming subscriptions. Sarah's younger, maybe still rocking her old playlist, while Sam's moved on to dad jeans. This isn't just a thought experiment. Tests with super precise clocks on fast-moving planes and particles in accelerators prove it. Time really slows down when you're speeding along, though you'd need to hit crazy speeds to notice it in everyday life. Want to stay youthful? Book a rocket ticket, but don't expect an in-flight meal to make it worth it. Now let's get cosmic with something called cosmic strings, not the kind in string theory, but another wild idea. These are super thin, super dense threads of energy left over from the Big Bang, stretched across the universe like invisible cracks in reality. Think of them as cosmic zippers, so dense that a mile-long piece could weigh as much as a planet. If two cosmic strings crossed or vibrated, they could warp space-time enough to act like a gravitational lens, bending light from distant stars in weird ways. Some scientists think they might even create tiny ripples in space-time, called gravitational waves, which we've detected from things like merging black holes. Einstein's general relativity didn't predict cosmic strings directly, but it allows for them, and they could help explain how galaxies formed or why the universe looks the way it does. So far, we haven't spotted any, but astronomers are on the hunt, scanning the sky for their telltale effects. Then there's Kurt Gödel again, the mathematician who hung out with Einstein at Princeton. In 1949, he cooked up a solution to Einstein's equations that's straight out of a sci-fi novel. Gödel imagined a rotating universe where time loops back on itself, creating paths called closed time-like curves. Follow one, and you'd end up in your own past, like hitting rewind on your life. It's as if the universe were a vinyl record with a scratch, making the needle jump back to an earlier song. Our universe doesn't seem to rotate like Gödel's model, but his idea showed that Einstein's equations don't rule out time travel. This shook up physics, suggesting time might not always flow forward. It also sparked debates about whether the universe has built-in rules to stop you from messing with the past, like a cosmic bouncer keeping history safe. Now, let's look ahead to the future of life in the universe. Einstein's work, from the Big Bang to black holes, sets the stage for big questions about where we're headed. The universe is expanding, pushed by dark energy, that mysterious force tied to Einstein's old cosmological constant. If it keeps speeding up, stars will eventually burn out, galaxies will drift apart, and the universe could become a cold, empty void in trillions of years. It's like a party that runs out of snacks and music, leaving everyone to go home. But life might find a way. Advanced civilizations could harness energy from black holes, using their intense gravity to power megamachines. Or maybe we'll figure out how to hop to other universes, if they exist, through wormholes or other cosmic tricks Einstein's equations hint at. It's a long shot, but his ideas make us dream big about humanity's place in the cosmos. Speaking of other universes, let's talk about brain worlds, a concept that builds on string theory. Picture our universe as a flat sheet, a brain, floating in a higher dimensional space, like a piece of paper in a stack. Other brains could be nearby, each with its own physics and maybe even its own life forms. If these brains collide, the energy released could spark a new Big Bang, creating a fresh universe. It's like shaking a snow globe to start a new storm. Einstein's relativity doesn't predict brain worlds, but it inspired string theory, which needs those extra dimensions to work. If true, our universe might be one of many, each with its own rules, and we're just a tiny part of a cosmic multiverse. Dark matter and dark energy come up here, too. Dark matter, that invisible stuff making up about 27% of the universe's mass, clumps around galaxies, helping them hold together. It's like the glue that keeps the cosmic furniture in place. We can't see it, but we know it's there because it bends light and affects gravity, just as Einstein's equations predict. Dark energy, about 68% of the universe, is the force driving the expansion, pushing galaxies apart like a cosmic accelerator pedal. Einstein's cosmological constant, which he once ditched as a mistake, turned out to be a genius guess for explaining this. Together, dark matter and dark energy shaped the universe's fate, and Einstein's work gave us the tools to understand their effects, even if we're still figuring out what they are. What about the endgame? The universe's expansion suggests a future where everything spreads out, cools down, and fades away. But there's a twist. If we ever crack quantum gravity, blending Einstein's relativity with quantum mechanics, we might unlock secrets about the universe's structure. Maybe we'll find ways to manipulate space-time, like bending it for faster-than-light travel. Well, not really, since Einstein says that's a no-go, but maybe through wormholes. Or perhaps we'll discover that time and space aren't fundamental but emerge from something deeper, like how a picture emerges from pixels. These ideas stem from Einstein's legacy, pushing us to ask what's possible. As a grand finale, let's reflect on what Einstein's work means. His theories, special relativity, general relativity, and even his tussles with quantum mechanics, changed how we see reality. Time isn't a steady tick-tock. It bends, stretches, and maybe loops. Space isn't a blank stage. It's a dynamic player, warped by mass and energy. From GPS in your car to pictures of black holes, Einstein's ideas power our tech and fuel our curiosity. He didn't solve everything. Quantum gravity and the nature of dark energy are still mysteries, but he gave us a map to explore the unknown. The twin paradox shows us time's personal side. Cosmic strings and Gödel's loops hint at its weird flexibility. Brain worlds and dark matter stretch our minds to consider multiple universes and invisible forces. And the universe's future, whether a cold fade-out or a bold leap to new realms, ties back to the questions Einstein dared to ask. His life, from a patent clerk to a Princeton icon, wasn't just about equations. It was about challenging the status quo, dreaming big, and leaving us with tools to keep pushing forward. In the end, Einstein's story is our story. His work reminds us that the universe is stranger than we can fathom, but it's ours to explore. Whether we're chasing cosmic strings, pondering time loops, or wondering about life in a multiverse, we're standing on his shoulders. The universe keeps expanding, and so does our quest to understand it, thanks to a guy with wild hair and a knack for asking the right questions. Want to keep exploring these cosmic mysteries? Subscribe to the Midnight Paradox channel, where we dive into the wildest corners of science, from time travel to multiverses. Join us, and let's unravel the universe together.